everybody, and welcome to this week's episode of Echo Live. My name is Anna, coming to you, of course, from the Michigan Science Center's Echo Distance Learning Studio. Today, we're going to be talking about some up-close science, and I mean literally up close. We are going to be using one of my favorite science tools, which is an inexpensive handheld microscope, and we're going to take a look at things on a level that our eyes just aren't able to see. It's going to be a pretty cool program. So before we get started, as always, if you haven't done so already, go ahead and introduce yourself in the chat feature wherever you are watching from. I can see some friends starting to join in on Facebook. Hello to all of our friends who've already said hello or let us know that they are here and that they are watching. Hi to those who are tuning in on YouTube and right here in Zoom as well. Remember that the chat feature is your best way to communicate with me throughout the entire show. You can answer questions, you can ask questions, you can give us some reactions. Hi to our friends in Zoom from Minnesota. So happy to have you all here joining us for our episode of Echo Live this week. All right, so let's get started by talking about some of the science that we are looking for during today's program. Now, way back over the summer, if you weren't here for our Echo Live programs over the summer, we did an entire episode on crystals. We talked about how crystals formed. I got to show off my rock collection, which I am super passionate about. But before that episode, I really didn't know a whole lot about the science of crystals. I always thought they were cool to look at, but I had no idea how incredible the science was when you got down on a microscopic, or even further than microscopic, on a chemical bond level. Hi to Mrs. Worth's class in Sacramento and Herman Leinbach Elementary. Hi, everyone. Thanks so much for introducing yourself. So let's do a quick review of some basic crystalline structures, because all the things we're going to be looking at today have pretty interesting structures, which we'll get to see under the microscope. But I thought it'd be a good idea to do a quick review of some different types of crystals that we see in nature or that we can grow in a chemistry lab. There are 6 or 7, depending on which scientist you ask. We love to make things more complicated, but there are usually 6, sometimes 7 basic shapes that crystals can grow in, meaning that atoms and molecules rearrange themselves to pack themselves down tightly into shapes just like the ones you see here on the screen. First, we have cubic, and it looks just like what it's called, looks like a cube. We also have tetragonal. We have triclinic, which I think looks like a small house. We have orthorhombic, which is quite similar to cubic, except that it's not a cube. It's not equal heights, length times width times height, but it's a bit longer, or at least away from the screen from the direction we're looking at it right now. There's also hexagonal, which is a shape that has 6 sides, but this one has 8, right? Because we count the top and the bottom as another shape, but 6 exterior walls. We have monoclinic, which is quite fancy. And then we have trigonal. So just keep these shapes in mind as we move through our program today. But really what we're trying to do is I just want us to take a look at some substances that we've probably seen on a macroscopic level or on a large scale, and take a look at it under a handheld microscope. So right here, I have a handheld microscope. It's got a light attached to it. Which helps us to be able to see a little bit better when we're really zooming in up close. It's just powered by a USB, which is allowing me to connect it into the computer. And then it just basically is a really high-powered camera inside this tiny little device right here that we can use to take some up-close looks at our various things that I have collected that I think look really cool under the microscope. I thought I'd talk about a pretty important crystal that most of us, if you live here in Michigan at least, and maybe other parts of the country too, are probably experiencing right now. We're going to talk about ice. And I know here in Michigan, or at least in Southeast Michigan, where I live, we got our first major snowfall of the year. It wasn't a lot, but go ahead, tell me in the chat. Do you have snow or ice on the ground where you live today, or have you gotten any so far this year? I know it's not quite scientific winter yet. We haven't quite passed the point where we would consider it to be true winter, but in a general sense, I consider once there's snow on the ground, it's just about winter time for me, and I'm pretty excited about that. So I'm going to go ahead and we're going to take an up-close look at my plate full of ice cubes here. I'm going to switch my camera over. And now we've got the zoom in. You can see that right now it doesn't look like a whole lot of anything because we're not focused and we don't have our camera pointed directly at our specimen. I'm going to go ahead and turn my virtual background off so we don't get any sort of interference. And let's take an up close look at our ice cubes. Mrs. Worth's class said that they don't have snow quite yet, but just frost, which means snow is probably coming your way pretty soon. So here we're taking a microscopic look at ice. And you can see that clearly we need to do some cleaning of our ice maker here at the Michigan Science Center because I'm seeing some tiny, very tiny, definitely can't see them with my naked eye, but there are definitely some dirts and specks of dust on my plate and in my ice cubes. Now, ice is very interesting, water ice specifically. Water ice has one of the strongest crystalline shapes. Now, generally when we think of our states of matter, we think of when things go from being a solid to a liquid, like we're seeing on my plate here, to a gas, like in the air. Generally, we say that atoms and molecules start to expand or take up more space. But ice is a really interesting exception to that rule. Because of the crystalline structure of ice, ice actually takes up more space as a liquid. Because when these H2O molecules are locked in to their shape like this, they actually fit together much more carefully and much more closely. Now, with my naked eye, I can't see any of these bubbles in this ice, but under our microscope, they're actually quite large. So this, like we said, is water ice, and water ice is frozen or compacted H2O. 2 hydrogen atoms, 1 oxygen atom, all in one molecule, and those molecules then hook together to form themselves into some different kind of structures like we see in this diagram here. Now in this diagram, I have water ice or water crystals over here where we can see those hydrogen bonds are connecting them. So you can tell these are H2O molecules because there are 2 small molecules, 2 H's and 1 large oxygen molecule. And then this shows us how those molecules all hook together into their crystalline structure. Hydrogen atoms are attracted to oxygen atoms, and oxygen atoms are attracted to hydrogen atoms, and the pattern goes on and on and on. And so the interesting thing, I think I misspoke opposite earlier, is that this actually takes up a lot of space. So normally we think of when things get warmer, the molecules will start to expand, they start to grow. But in the case of water, when these crystals melt into liquids, they're actually able to get much closer together because these bonds keep them at an exact distance. So ice actually takes up way more space than water does. And I apologize if I said that backwards earlier. I think I was thinking my facts backwards. Now on the other side of the screen though, we have a different type of ice. We normally think of ice as water ice because that's the type of ice we get on the ground thanks to the water cycle here on Earth. But this is actually frozen carbon dioxide, which we might also know as dry ice. We call dry ice just that because it never melts. It never goes through that phase change of turning from a solid into a liquid. And this ice is much, much colder. So let's go ahead and take an up close look at dry ice. Need to stop my share, pick up our Zoomy, and let's take a look. Now this looks very different under our microscope. There's a distinct difference between the arrangement of these crystals or of these molecules in our dry ice, our frozen CO2, than with our water ice. You could even see it kind of starting to fleck off the side, but there is much more air trapped inside this dry ice, this frozen carbon dioxide. You can see it on the camera, and I can even feel that this feels much less dense. So because of the crystalline structure of carbon dioxide, there's a lot more gaps in between these molecules. And so these molecules leave a lot of room for air pockets, which makes their structure very unique. Now I've got one more type of interesting chemical when we're talking about snow and talking about ice. is on the tray on my table here. I also have something called Insta Snow. And Insta Snow is not made out of anything that's frozen. It's not made out of carbon dioxide or water. This stuff I have on my tray here. Give you an up close look. This stuff I have is actually made of a super absorbent polymer. To the naked eye, it looks just like snow, but my first observation from touching it with my hands is that it doesn't feel like snow at all. It's very, very soft, it's quite fluffy, but most noticeably, this stuff is not at all cold. It's actually just about maybe slightly lower than room temperature. So this is certainly not a solid or frozen form of anything. This is actually a super absorbent polymer. This polymer, when it touches water, actually absorbs the water and then grows. Those molecules inside rearrange themselves to be about 100 times their original size. So let's take a look at this stuff up close. And I can see we've got some questions coming in. Anthony would like to know, would water and ice plus mint make it colder? That's a great question. Would adding mint make it colder? I think the misconception is because mint has kind of that distinct kind of stinging feeling to the tongue, it doesn't actually get colder. Temperature is just a condition of how much energy a substance has. So temperature is just evidence of kinetic energy. If there's a lot of kinetic energy, and there's an easy way to demonstrate this at home or in your school, wherever you're watching from, if you go ahead and rub your hands back together, having a lot of kinetic energy causes a lot of molecules to bump into each other or cause friction. And if you're doing this like I am, my hands are starting to get quite warm. And so having more energy can be observed as more heat or more thermal energy. It's just evidence of atoms and molecules moving quickly or having more movement. Adding mint to a substance, though, does have an interesting effect on any sort of solid. Now, generally, when we're talking about ice cubes, we want to drink just regular, pure water, right? But we know that there's all sorts of minerals in our water. Some of them are there to keep us healthy, things like fluoride for your teeth. There are other substances that we put in the water to keep substances on our pipes and to make it safe to transport. Sometimes we put vitamins or minerals in the water for added health benefits. But adding anything to water will actually lower the freezing point of that water. So it will need to get much colder if you were to add mint to water if you wanted to freeze it into a solid. If you only add a little bit of mint, it might not be noticeable, but the more impurities you add to water, the more you're going to drop the freezing point, or the colder it will have to be before it turns into a solid. So that's a very interesting question, Anthony. All right, now we've got a few different substances here on my table. All of these are different types of powders or household solids that I've gone ahead and dyed blue. Some of them are bluer than others, but that could also have to do with their structure and how well they can absorb the food coloring. So in our first one, this is a small amount of salt. And salt is our first real true tiny crystal we'll get to look at today. So let me go ahead and switch my camera. And I'd like for us to take an up-close look at the salt. Now you can actually see the individual salt crystals here. They're pretty similar in size. They're very, very consistent. Let me see if I can get my microphone to focus even better than it is right now. There we go. Here we go. So take a look at these. We can see that some, even though from far away, the entire container of salt looks blue, when we take a look up close, it's actually quite a different spread too. So not only are we able to see all those individual individual crystals of salt, we can actually see that some of them must not have come close enough or gotten enough food coloring near them, because some of them are still clear, while others are various shades of blue. So especially if we go towards the edge of the container where I probably didn't do as good of a job stirring, you can see all those various structures. So let's take this back to our diagram. So everyone keep this image in your mind, and I'll try not to let my hands shake the camera, but keep in mind how zoomed in we are. My hands don't appear to be moving to me, but even my heartbeat is enough for you to see this movement in the camera. But I'm going to pull back up our picture here of our different crystal shapes. And I'd like if you had to pick one of these crystal shapes and tell me what type of crystal or what shape of crystal we are growing, why don't you go ahead and tell me in the chat? And let's see, question from Mrs. Worth's class, why do they look blue? Good question, Otniel, and you might have to tell me if I said your name correctly. They look blue because I dyed them with food coloring. Now, the food coloring that I use is actually water-based. And so this food coloring can actually only dye things that are hydrophilic or will absorb water. And so you can see that I added blue food coloring. Salt must be hydrophilic. It must love water, be able to absorb water, which is why it was able to absorb that beautiful blue color. Now, it might not be the easiest way to classify shapes, and salts can grow in all different types of patterns and structures. If I had to base my guess on this image, I might say that this is a hexagonal or six-sided type of crystal that we are looking at under the microscope. But the interesting thing about crystals is that they can actually decide to be different shapes based on the conditions where they were created. These conditions could be out in the ground when we're forming things like geodes or diamonds, but it can also happen in the lab. And scientists are very interested in how to grow crystals in the lab, not just for jewelry, but also for scientific purposes. Also for electronics and all that stuff. And so what scientists have found is that when diamonds are grown either in nature or in a lab at very high temperatures, they actually grow in this octahedral or eight-sided shape. Whereas if they're grown at colder temperatures, they're more cuboidal or cube-shaped. So different kind of conditions where this salt was grown could also affect how these crystals look or what shape they grow in. Let's take a look at our next substance. To the naked eye, it probably looks very similar, but way up close, this one looks pretty different. This is sugar. And you can see that these crystals are much more irregular, that they're not all the exact same shape like our salt was. We have kind of some square ones. I can see some round ones. Some are quite large, whereas some are quite small. So the color is quite similar, but their shape is very, very different, which is really cool to look at under the microscope. One of the reasons for that is that this was probably a big block of sugar that was then chopped up into tiny pieces or ground. And so these aren't the actual crystalline shapes of sugar, but these are the remnants after we've shredded a much larger crystal. So under a microscope, it looks very, very cool. All right, our next one is borax. And if you are a slime making expert, which I'm sure many of you are out there, borax is great to use as a polymer or a cross-linker for making slime. Ooh. Oh, thank you, Otniel, for telling me I said your name correctly. A couple of people were guessing cubic, which I would agree with too. So borax crystals, again, much more irregular. The reason is the same as with our sugar, is that we can grow borax or create borax in large, large clumps, and then we usually grind it down into a fine powder to be used as a soap. And you can see that process isn't perfect. We can see all sorts of imperfections, different sizes, different shapes, different levels of absorption with that blue food coloring here inside the dish. We have this one here. This is cornstarch. And when you mix cornstarch and water, you get one of my favorite chemical substances, which is oobleck. So if you have any cornstarch at home, you can make your own oobleck, which is pretty cool because just like slime, it's a non-Newtonian fluid, meaning it behaves like a solid sometimes, but a liquid at other times. I didn't add quite enough water to this one to make it into oobleck, but just enough to have it absorb that blue color. But you can see that these flecks of cornstarch is a much finer powder. It's very, very soft and fluffy and very, very tiny. Anthony asked another great question, which is why does salt stick to people when they touch it? And we've already talked about this just a little bit. We said that all of these substances, if they absorbed the food coloring, must be hydrophilic or love water. Hydrophilic means loves water, and hydrophobic is the opposite, which means dislikes water. So hydrophilic substances love things that have water. They want to stick to them, they want to bond with them, they want to be part of them. And salt is one of those substances. And you might know that humans are made up of lots of water. Even if you can't see it, there is microscopic amounts of water all over your skin. That's a good thing because it keeps your skin nice and hydrated. Sweating helps your body to temperature regulate or cool down. And so not only is it about that, not only does it stick because it loves the water on your body, but this structure, right, is really good for sticking to all the tiny little divots and grooves and hairs that are all over your body. Even in places you might not think you have hair, your body is still covered with a very fine layer of fuzz. So if we take a look at my hand, for example, the back of my hand, even the back of my hand, you can see almost has things like fingerprints. They almost look like fingerprints, but there's also hair. And so the salt can also attach itself to all these tiny, fine little divots and grooves inside your body, or specifically your fingers, right? We'll talk about fingers in just a moment. Now I have one last blue substance here. This last blue substance is kinetic sand. And kinetic sand, I actually was not able to dye blue with food coloring. This one I actually bought this color from the store because unlike salt and sugar and borax, kinetic sand is hydrophobic. It hates water, which is actually what makes it so fun to play with. Now you can see just how tightly packed all these molecules are together. Let's see, I'm going to pick just a little bit of it up here, put it on my hand. But you can see that they are very, very tiny and very, very tightly packed together. So this stuff is hydrophobic. It does not like water. And so they actually had to dye this with a different type of gel-based dye or oil-based food coloring in order to turn it this blue color. So this is our only hydrophobic substance that we have here to look at today. Ooh, Amy, let's see here, Mrs. Worth's class. Kamari asked, are diamonds clear and do they add food coloring to make them clear? That's a great question. Diamonds are clear when they are incredibly pure. So if we think back to my slide here, the temperature didn't do much to affect the color, right? The color is the same, but the shape was different based on temperature. But having different types of impurities, different types of minerals, just like we talked about with the water that we drink, having those different types of minerals also can affect the color of your diamonds. So diamonds come in other colors besides clear. There's yellow diamonds, pink diamonds, but diamonds are basically just crystallized carbon. If it's pure carbon, just carbon, no imperfections, nothing else, most of those diamonds are clear. We can't dye diamonds with food coloring because all the food coloring would evaporate away immediately. Because diamonds have to be grown under incredible temperatures and incredible pressure, whether that's in nature, like we see here, 2,200 degrees Fahrenheit, or whether that's in a lab under using some special equipment. That is a fantastic question. All right, I've got a couple more items for us to take a look at. This is still on my kinetic sand there, which I think this is my favorite one to look at under the microscope. But we're going to move on and we're going to talk about some different types of materials. Now on my table, if I switch my camera back, I have a rock. And this is by no means is it a crystal or a geode. It's just a regular old rock, but even regular old rocks have some very interesting things to look at on a microscopic or at an up close level. Now, even though if you were to look at this right now, it all looks pretty consistent. Most rocks are actually a combination of many different types of crystals all in one. So let's go ahead and switch our camera back. Take a look here, and you can see all these different types of crystals that are formed together because the ground or the earth, right, is full of minerals. And minerals like to stick to themselves. You can see that we've got some large clumps of crystals or like substances surrounded by others because the ground is full of crystals all growing at the same time. And then sometimes they form into larger structures like this once they run into each other. Unfortunately, once they run into each other, they can't keep growing in their crystalline shape, but they can still kind of turn into, under enough pressure, into larger clumps of rock, just like the one we see here. So I highly recommend the next time you find a rock and it doesn't look like anything special, take an up close look. If you don't have a handheld microscope like this one, you can still take a look under a magnifying glass, or you can look at it maybe up close if you have a cell phone camera, but all sorts of very, very interesting details can be seen when you look up this close. Now, organic materials can also be very interesting under a microscope. I have a pine cone here, which I keep doing this, like you can tell that it's a pine cone from this far away. But this is a pine cone, but I thought it would be fun to take an up close look at this too. Because just like our rock, and just like some of the other things we've talked about, these look very different up close, and look how much detail there is that you couldn't normally see with your naked eye. Now, the fun and interesting thing about organic material is that these were once living things too. This pine cone was once alive. The wood of my table was once alive. Now, when we look at things this close, right, one of my favorite things to look at is something like a fingerprint. So this is my pinky finger here. And let me see if I can hold it still enough with only one hand that we can get an up close look. But fingerprints are very unique. Everyone's fingerprints are different. Even identical twins have different types of fingerprints or different sets of fingerprints. But there's all sorts of shapes and patterns, and you might even, since you have your own fingers in front of you, you might even be able to see your own fingers up close. And my hand looks clean to me when I look at it, but look at all of that borax or salt or whatever it might be that's on my finger that I couldn't even tell. So taking an up close look sometimes reminds us that there are microscopic germs and microscopic dirt all over us all the time, which is why it's very, very, very important to wash your hands. But just like people have very unique and identifying fingerprints, so does other organic material. The grain of wood that you see here on my table is specific to this living tree. We could zoom in even farther. Let's see if I can get it to focus. My light doesn't seem to be working when it's that close, which is pretty weird. If we get it to zoom in, this specific pattern or grain of the wood where you see all those cuts and divots, that is unique to this living tree. No two trees grow the exact same pattern on a microscopic scale. Same with my pine cone. If I were to look at each one of these petals, each one of these seeds would have its own pattern of divots and grooves all over it. So people and scientists tend to study these things because we think from a macroscopic, again, from an outside view, that all these things really look the same. But when we take an up close look, we can see that they look very, very different. Now, I think we talked about fingerprints a little bit, and I'm sure a lot of us have heard this phrase that no two fingerprints are alike, and that's true to an extent, but not true to an extent. With all of the billions of people that live here on Earth, it's entirely possible that someone has the same one fingerprint as someone else, or at least very, very close. What is unlikely is that you would have your entire set of fingerprints exactly identical to another of the billions of people that live here on Earth. And so I'm sure we've all heard the phrase, though, too, that just like no two fingerprints are alike, neither are any snowflakes. And so snowflakes are another really, oh no, I hope I have it. There they are. Snowflakes are another very beautiful thing to look at under a microscope. Now, this handheld microscope isn't quite powerful enough to see the individual crystalline structures that we see here. But thankfully, scientists have been taking these beautiful pictures for many, many years, showing us that snowflakes are very different from each other. They grow in all sorts of shapes and patterns with holes and divots and gaps all inside them. And so they are absolutely right that snowflakes, it is unlikely that you'd ever find two of the same snowflake that are exactly the same. Is possible, not likely. All right. This is just about the end of our time together today. It's just about 3 o'clock. But of course, if anyone has any other questions, especially for Mrs. Worth's class, I can see lots of people having great questions from over there. Hi to our friends watching in Hamtramck. If you're still there, if you have any questions about the crystals or the microscope that we've talked about so far, let me know in the chat. I'd be happy to answer a few before we go. As always, at this point in the program, we'll say thank you to Ford and Denso for sponsoring Echo Live all through this year. We'll continue seeing you here every Wednesday. And so, of course, our schedule is every Wednesday at 2:30. If you have suggestions for science experiments that you want us to try or things you want us to do here on Echo Live, let me know. I love to have suggestions. I love to talk about science that is related to things you're learning in school, or just things maybe you aren't learning in school and you want to learn for fun, because science is really supposed to be fun. And that's why I love my job so much. So I don't see any questions coming in just yet. That is okay. If you do have questions after the program, or if you're looking for more science that you can try in your classroom or at home, you can visit the Michigan Science Center's website. There's a great resource here. mi-sci.org/at-home-science is a great place to find activity guides, experiment suggestions. You can also find contact information for us there. Feel free to send us a message, ask questions, tell us what you think about Echo Live. Oh, I see a question coming in just now. But definitely check us out, and we hope we'll see you back here next week. Let's see, Lizith, sorry about that one. Lizith said, what makes snow fly so thin? Snowflakes are very, very thin because, again, of that crystalline structure. It's easier for water molecules to attach themselves where they find the nearest spot where they can hydrogen bond. So if you're talking about snowflakes being very thin, that again has to do with that structure that we looked at, where oxygen will pick an hydrogen atom and a hydrogen atom will pick an oxygen atom, and they can become flat, flat, flat like a pancake. But if the conditions are right, they might grow taller, they might grow wider, but then snowflakes will also stick to each other. So if you go outside and you try to take a look up close at a snowflake, you'll probably have a very, very hard time getting just one snowflake, because once those oxygen and hydrogen atoms come near each other, they lock together, they hydrogen bond, and they want to stay that way. And so it's very difficult to get just one snowflake unless you catch it falling from the sky. So if you do that, you might be able to get an up-close look before the heat of your hands will melt it. Let's see. Isban said, are crystals hot or cold? Good question. Most crystals have to be formed under hot temperatures, under a lot of pressure and a lot of heat. But once we pull them out of the ground, just like a rock, they usually feel pretty cold to the touch. That's because most of them are very good conductors of thermal energy or of that kinetic energy. So they'll actually borrow the heat from their environment. That environment could be the weather outside. It could be from the human that's touching it, since we generate thermal energy as a product of all the chemical processes in our body. And so they generally feel kind of cold to the touch, but that's usually once they're done growing. So they can be hot or cold, depending on where they are, because these are not living creatures. They don't have the ability to thermoregulate. They are not alive, and so they don't make heat or use heat, but they can conduct it. So it really just depends on where you find them. Good question. Ooh, let's see. Nathan said, how do snowflakes form into so many awesome different shapes? And that, just like the diamond we looked at, has to do with where they grow. It has to do with the atmospheric pressure outside. Now, right now, there's actually 14.7 pounds per square inch pushing on your body. That's enough to crush a car, but thankfully, there's enough air inside your body to make those two pressures equal. But pressure behaves differently depending on your environment. And so some crystals are grown under a lot of pressure, some under less, and even the very small changes in pressure outside can be enough to change the conditions where your snowflakes were grown, which is part of the reason that snowflakes can look pretty different from each other, which is really cool. Good questions, everybody. All right. If you continue to have questions, send us a message. You can keep commenting on this video. You can send us a question on Facebook. We'll answer one more before we head out because Anthony asked something pretty related to our last question, which is, are diamonds colder than crystals? They're the same because diamonds are crystals, but instead of being made out of carbon dioxide, like our dry ice, or sodium chloride, like our table salt, they're made out of carbon. So carbon is just another one of those atoms or elements on our periodic table, and they form into crystals. So diamonds are crystals, just like Alondra said, which is why diamonds are just as cold or just as warm as crystals, because they're all crystals. Just they all look different, which is what makes rocks so, so cool. All right, everyone, thanks so much for tuning into Echo Live. I hope I see you back here next week for another episode. We've got a really fun space program planned. So if you love space, you won't want to miss it. We'll be talking about craters and some different fun space facts. So I hope I'll see you all then. Until then, have a great rest of your week.